Yeah, I think we can start. Somebody else can join.
Well, okay.
Okay. So this is a correction for the masterclass. It's number 17, and I think Samuel will go through the correction step by step. That's it. Easy.
Yeah, easy. Okay, so I'm just gonna walk us through. Let's share this and move this over. Are you guys seeing the masterclass course?
Yes.
Perfect. Okay, so assuming that everyone could successfully do the installation, which I think maybe could have been a problem for some people, we'll just move on to going on to the first tutorial, which is the single structure refinement. And just to remind everyone, you can find this GitHub repository through the PLUMED Masterclass webpage. Okay, so the first step in doing this procedure, which this first tutorial is to generate a structure for the best single structure that fits your Cryo-EM density map. Particularly, we're working with the Tau 1A fiber system that was determined by the Schurz group. And in order to, yeah, I'll just walk us through starting with step 0, which is really the system setup. So the first thing we want to do is, what we were doing is we were going to Charm GUI, the web server, downloading the PDB. So in this case, PDB 7P6A, loading into the Charm GUI and correctly developing the environment. For this tutorial, we've already done this stuff for you. So you have the step 3 input.grow, which is the file produced by Charm GUI. But if you wanted to, you could produce that on your own. One thing that I think is worth noting is that potentially when Charm GUI generates a structure for you, it might have a different location than in your deposited PDB. So if I go into here and I load up our structure that we're going to be looking at, let me copy this. I can just show the difference between our two structures. If in the map preparation folder, we should have your deposited PDB, which we see here. Sorry, let me change them. And then if we load in the structure generated from the building procedure, which is step 3 input.grow, we can actually see that it's translated and slightly rotated in space. So one of the first things that we end up doing is trying to move, we have to move this back, and we need to make sure that Charm GUI does not renumber everything. So the first step we do is to run the script that we created called renumber.sh to maintain the same atom order as in the deposited PDB. Later on, we'll worry about the translation step, but for now, we just renumber the PDB and make sure it's the same as the deposited 7P6A. From here, we then select the atom groups that we're going to be using throughout this process, which are the atoms that make up the Cryo-EM density map, and a selection that we write to the output file. So the first selection is really the system map, which is again, as it's stated here, this contains all the atoms you use to generate the Cryo-EM density map. So this will be any molecules that you want to model. So in this case, we're just doing the protein, but you can imagine if you have a ligand present or ordered water, you might want to include those as well. So that can be done using this make NDX file, using a selection. So in this case, it's just the protein, and then we end up with system map, the selection system map inside our index file, which I won't show because I think everyone's pretty familiar with that. Lastly, we create a system XTC file, or a system XTC group. And again, this will just be the molecules that we write out during our trajectories. So now once we have the structure built, we move on to the map preparation. And this part is, I think, one of the key steps to this whole procedure. First, we need to download this initial Cryo-EM density map from the EMDB. And the 2 half maps, preferably. By downloading the 2 half maps, we can then get some measure of error between the maps, which Max had discussed about last week, which helps us create a lower bound for our restraints. So in this step, this Cryo-EM pre-process map does a couple of things. Number one, it zones the map, taking just the Cryo-EM density around the the PDB instead of taking all of the density within the Cryo-EM density map. So I'll just show you here why this is kind of important for this system. Because if so here's our structure that we have this week, which is these 5 chains inside this fiber. And if we load the Cryo-EM density map in the same session of Chimera X, we can see that Cryo-EM density map is actually much larger than the 5 chains. We don't really want to model the rest of this, so it's kind of important that we do zoning just to zone around the molecules, the atoms that we have. So again, this can just visually, we can see this if we do a surface zone around 3.5 angstroms, which I think is what we used for this tutorial. Whoops, sorry, I need to select the atoms. We end up with a selection of density around this structure. In this case, you can see that there's kind of some artifacts because this is a repeating chain. You have density left over that potentially belongs to the neighboring chain. So you might want to actually even tighten this zone even more to a smaller cutoff. But in general, this zoning procedure, even if you don't have a structure that looks like this long fiber, is good because it's going to save you a lot of computation by trimming the system. Don't need that. Right. Well, the other thing that this is going to do is it's going to take your 2 half maps and generate an air value associated with them. So the difference between the 2 half maps is going to generate air for each density voxel, which will then be used as the lower bound during our refinements, the plume process, the actual plume process. And the other important thing that this step does is it actually removes the correlated voxels within our system. So I don't know if Emma's the only one here, but I don't know if anyone in the future will be doing this. So I'll just show you. This value here changes the correlation cutoff that you use. So in this setting right now, we remove all voxels present in the Cryo-EM density map inside our zone that are correlated with the correlation greater than 0.9. You can test this and play with this. I think we've played around with it, and we think that around 0.8 is a good value for the correlation cutoff, although this might change depending on your system. What we can see, whoops, not on this screen, but what we can see here is I did three tests here, or 4 tests actually, with different correlation cutoff values, and you can track the number of voxels that are discarded during the process, the plume process. And what we see is that initially at 0 correlation, you have, or at 1 correlation cutoff, of course, there's no voxels removed. At 0.9, you have very few voxels removed. And as we move into lower and lower correlation cutoffs, we're removing a significant amount of voxels, which does mean that there's a lot of correlated data within these Cryo-EM density maps that potentially is not needed. What this will end up looking like inside the file, once we run this, we're going to get an output file called log preprocess. Sorry, this is the wrong. And this log preprocess will have a lot of this good data that we're interested in seeing. So it'll have the number of voxels present in your Cryo-EM density map, the zoning cutoff that you use, the resolution of your map, the number of atoms, voxel size. And interestingly, it'll have this median density, the integral of your density, which is going to be important later for how much density is present inside the Cryo-EM density map, and the number of voxels present per atom. And down here, we can see the number of percent of voxels discarded. So again, as we increase the correlation cutoff or decrease the correlation cutoff value, we end up removing more and more correlated voxels. And we think that this to some degree does increase the quality of our map because you need independent data points. And a lot of these data points are not adding anything to our simulation. And they can also, in the future, if you can imagine adding in different sources of data and properly weighting these density points can actually lead to incorrect ensembles. So it's important, again, to remove correlation between these voxels. Once we have done this, we end up with an initial plumed map, which will just be this EMD plumed.dat, which will have your density voxels, or the position of the voxels, the density, and their associated air. Last week, someone asked what happens if you don't have the two half maps present. In that case, this column here on the air will just go to 0. This potentially can give you some decreased accuracy inside your simulation, but for the most part should be okay. You'll just have a air value that is, I think 20% of the median voxel density inside your system. I know there's only 2 of you, so hopefully that's clear, but I'll get into that more later. But you can run this without having the 2 half maps. It should be okay. But if you do have access to the 2 half maps, you should get a better ensemble. From here, then we need to actually go back and fix the issue I was talking about earlier, where the charm GUI will potentially translate and rotate your system away from the initial PDB and away from the location of the Cryo-EM density map. So we need to end up moving the plume density map to where our charm structure is. And that's what this Python aligned voxels script will do for you. And it will align this based on your reference selection. So in this case, our reference is the step 3 input PDB, which we generated, and the mobile selection will be the deposited PDB. We make a selection and we do an alignment based on the same number of atoms. And what you should end up getting a very, very low RMSD. If you don't have a low RMSD, you should check your selection and your alignment of your 2 structures, because something is probably off, and that will throw off your simulation. So again, you should have very, very good alignment after you run this step, and this should be output to your screen once you run this script. Okay, so this will also generate for you again the same plumed file, except now it will be moved and aligned to your structure, the simulation structure that you're going to be using. So the system that you're going to be using, the step 3 input. So again, same thing, but different locations of the voxels. Is this any questions for the current group? No.
I'm fine, thank you.
Okay. Max? No.
All clear, thank you.
From here, then we just proceed to doing a regular equilibration. So we're going to do a minimization with restraints, but not the Cryo-EM restraints. Again, it's important to have some restraints so that we don't actually move the location of our built system, so that it stays in line with the Cryo-EM density map. But we want to equilibrate the water around these systems. So we do a short energy minimization, followed by an NPT simulation and an NVT simulation. I don't think this is incredibly interesting to see, but you would just end up getting, again, typical files once you run these scripts. Your output, so we can just look at one of these log files, again, very, very typical Romax file. Then we start going into the where we start using the plume system. In this case, we go into the step 3, which is the map scaling. So again, if you think about how we trimmed the Cryo-EM density map, there was originally a lot more density present here in our system. Once we trim that, we actually decrease the amount of density present inside of our plumed ME system, ME density map. And so to make a correct comparison between our predicted Cryo-EM density map that's generated from our simulation and the experimental Cryo-EM density map, we need to rescale the density that we have in our Cryo-EM, in our plumed density map. So typically we're going to have to multiply our density by a number that's slightly greater than 1. And what we do in step 3 is we just optimize the scaling factor for our system. In this case, I think well, you can pick the different scales you want. Personally, I ran this at a scan from scale value of 0.5 to 1.5. I can show you, sorry, what this looks like in the actual plumed. The plumed file. And so what I'm talking about here is the scale factor value. So let me walk through this whole structure. So the first thing we have is the PDB structure. So this will be our selected atoms. In this case, it's just the protein, which will be exported here at the end of step 2. And this is just our what we see here. This is just the structure that's going to be output. From there, we want to define our system map, which is again the atoms that are going to be contributing to the cryo-EM density map here. In this case, it's just it's not used for that purpose, but this is what that is the system map. We then are going to just make sure this map is whole and not cut off by periodic boundary conditions, which is this script right here. So we run the whole molecules, which the commands can be found on the PLUMED website. And then we're going to create our EMI-Box environment. So here we have, we're starting EMI-Box, labeled as EMI. Here are a couple of parameters that again, it's labeled here, do not change. These were empirically tested, basically to increase the efficiency of our computations. Next, we do define, again, the atoms that are used for the cryo-EM restraints. So again, these are the systems that you want to be contributing to the cryo-EM density map that you have. Again, in this case, it's just the protein, but it could be the protein plus any number of things. And the data file that we're going to be using is this EMD plumed aligned.dat, which is, again, what we generated in step 1 in map preparation. Finally, we move on to this norm density. This is again this is calculated in the log file, which we can see right here is the integral of the density of our map. Then we have the resolution, which is going to be your resolution of your deposited cryo-EM density map, which is going to be used to generate initial B factor values for our simulation. We have data likelihood marginal, which is sigma min. This is going to be well, we can ignore this. I think for now it's used for some computations kind of inside the hood, but right now it's just shown because we're still working on development. This is going to be where we write our output file, so it's going to be called EMI status. We're going to write this every step because in this case we're doing a post-processing of our simulations that we generated in step 2, which is the equilibration. Finally, there's this command for if you have a hetero complex. You want to be modeling each chain individually. However, since we have a homocomplex, we have 5 chains that are identical. We want the B factors of each chain to be the same. So we have this B fact node chain flag here, which should ensure that each residue for each chain A, B, C, D, and E have the same B factor value. Finally, we do a B factor scanning, which should run through here. I specified a step size of 0.5, striding at every step. And finally, here's the scale value, which will be put in. So if we run the optimized scale script, it's going to pull off the norm density and the resolution values from the log preprocess file that I'd shown earlier that we generated in step 1. It will throw these into our plumed EMI BFACT template file, and then it will run the plumed EMI driver to scan, calculating the score of our system based on the given B scale value that we used. Hopefully this is somewhat clear. The result is going to be a bunch of files. So in this case, since I scanned from 0.5 to 1.5 at step size of 0.5, we have all these files here. If we take out the best scoring values, or the lowest energy score present in each of these Culver files. So let me go into one of these and we can see the output. So you end up with an ME status file, which will contain all your B factors. These stars present here mean that we have no chain, so it doesn't matter which chain you're part of, it just means that it's residue 282. And down here we have our B factor values, which are changing in each step based on our Monte Carlo scheme. Hopefully that's clear. Inside the Culver file, we have a number of different values. What we're concerned about right now is the score value, the ME score value, which is the overall energy of our system, which is the second column. And if we take the lowest energy value present in each of these, we can plot this as a function of the B scale value and determine the best B scale value for our production simulation. So this is all normally done automatically for you, so you don't have to worry about it. I just wanted to show what this can look like. So as you go to really low B scale values, we have pretty high energies. We end up seeing a minima around 0.3, 0.4. So you can scale this however finely you want. I think the difference is not going to matter after a certain point. Maybe 0.1 would have been a better choice because at this scale it doesn't really matter, but you could potentially even zoom in at finer intervals and see if you can get a higher score. Since there's only one person here, I don't think anyone did that, but yeah, if you're interested, you can always refine this even more, going down to a scale of 0.01. So again, what that means is that we have less density inside of our trimmed Cryo-EM density map, so we need to increase the overall density to make a comparison to the density within the deposit Cryo-EM density map. So this step will give you, running this script, the optimized scale, will give you this script, or this output file called best scale. In this case, I think this was run with step size of 0.1, so whether best scale ended up being 1.3. Finally, from here, we move on to the production of our simulation. And this is really what the meat of the single structure refinement. And it's very simple for us to do. First, we run this bash script, which is just to prepare the plumed input file, which I can show you the script right here. We can walk through it. So what this does is, again, it grabs the density from the log, the integral of the density from the log preprocess file, the resolution from the log preprocess file, and the calculated best scale factor that you just created. It then creates the plumed input file, which the template is very similar to the one we just observed. And now we increase the Monte Carlo B factor stride to 500 steps, since we are actually running a molecular dynamic simulation in the step. We don't want it to be we don't want to do a Monte Carlo every single step. Otherwise, this is the very, very similar structure to the last plumed input file. So again, you're going to be writing the output to this Culver file, which is typical, and you're going to be writing your ME score, which is that energy function that I had discussed earlier, every 4 steps. So from here, you end up then just running what is our production run, which is NVT simulation, with our plumed flag here, which is just going to run that plume script that I just showed you. This can be done with both CPUs and GPUs, but I think it's going to be much faster with using GPUs. So if you can, I recommend doing that. From here, you're going to get a single structure, well, a trajectory. This trajectory we can think of this as an uncertainty ensemble. In this case, it's really our structure, just trying to find the best single structure that fits this Cryo-EM density map, or really all the single structures that fit this Cryo-EM density map. This is in contrast to what we'll do next, which is the ensemble simulation. But first, before we do the ensemble simulation, we want to actually get the best structure that is resulting from this single structure refinement production run. So we go into step 5, which is the processing and validation. That's here in folder 5. And the first thing we do is we run this prepare plumed input emin, which is again going to take all the values that we've been taking before, the density, the resolution, and the best scaling factor, and it's going to start making a plumed input file based off of that. We're also going to extract the lowest energy frame from the single structure refinement. So it's going to take the lowest energy from the Colvar file, determine that frame, and we're going to end up generating a GROMAX file containing the coordinates of the atoms during that lowest energy structure. That makes sense. So you run your simulation in the production. The best scoring structure will be taken here along with its B factor values, and we'll write those values into this conf best.grow and the ME status score. ME status file will have the B factors. From here, we're then going to run a minimization, which we can see from this run plume emin, which is going to do most of this for you, but it's going to prompt your system, do a short minimization on your structure, so the conf emin. Next, we're going to do a plume driver. So once we've minimized the energy of our structure to basically fix any oddities that can happen within any given frame out of a MD trajectory, we want to make sure that there's no discontinuity in our structure based on the periodic boundary conditions, which is what this plumed driver, plumed fix PBC that does. Again, very simple. It's going to take our step 3 input XTC, so our protein structure. It's going to make it whole using the command in plumed. We again define our system XTC, which is the atoms that we've been writing to the output trajectory file. We're going to use the whole molecules command in plumed, and then we're going to dump the structure, which is going to be conf pbc.grow. From here, then we need to go back and realign our PDBs. So at this point, we have the minimized PDB structure that we've calculated during the step 4 production. And we're going to align this based off of the transformation that we calculated back in step 1 using this align voxels process. This is going to realign our PDB with the deposited PDB and the deposited Cryo-EM density map. From here, we're then going to add B factors back into our refined structure, which I don't think we need to go into the script, but essentially it's going to take the last column of your PDB. Sorry, this is conf. Over here, and it's going to add your B factor value that was calculated during our single structure refinement in step 4, and after the minimization in step 5. At this point, you have your final structure. This should be your refined single structure model. You can then test this using the do Phoenix command, which is going to do Phoenix and mole probabilities calculations on this deposited structure based off your Cryo-EM density map, given the resolution of the Cryo-EM density map. And your results are going to be written to this file results.plumed, which we can go into and see what we have. So we have our resolution of our maps, the CC box, which is the fit of our Cryo-EM, our model to the Cryo-EM density of the whole system. What we're more interested in is the CC match, which is the fit of our model to the Cryo-EM density around the protein. We also have other metrics here, such as the EM Ringer score, which is, again, measurement of side chain fit, RMS bonds and angles, Ramachandran outliers and favored, the clash score, which is the number of clashes per 1,000 atoms, and then the overall mole probability score. So just to show people what this ends up looking like for our structure here, I plotted for what I did on this system, I plotted the clash score, mole probability score, CC mass score, and EM Ringer score as a function of a number of different cutoffs, going from 0.7 to 1. What we see is that, again, using this method, we significantly decrease the number of clashes. In this case, with this tau filament, we've completely removed all steric clashes from the single structure refined models. We also significantly improved the mole probability score, which is, again, a better score. This corresponds to lower values on this y-axis here, with the deposited structure being shown in black for all of these. So this is good. Again, it means that we are scoring much higher on steric quality of these structures. We also have the CC mass score, which again is very comparable or slightly better than the deposited model at these cutoff values. And finally, we have the EM Ringer score, which is, again, is going to be better with higher values. I think we do fairly well in most of these structures, particularly when we maintain all the data. However, when we remove some of the correlated data, the score goes down. But in general, we think that a good compromise that we've found so far has been around 0.8 as a correlation cutoff value. So this, again, from here, you should have a refined PDB structure with a single model. Following these steps should be very straightforward. You can just pick any system that you're interested in, as opposed to the 7P6A. Download any structure that you want or any structure that you have in your in-house. Plug it into Charm GUI, generate a structure, follow this procedure, and you should be able to generate a single structure from that. Next, we'll move on to the structural ensemble, which is really the more interesting, well, I think the more interesting aspect of this MEVOX PLUMED tool. And this is going to calculate the structural ensemble for your model based on your Cryo-EM density map and your force field. In order to do this, you do need to run the first tutorial. You don't need to do the analysis of the first tutorial, but you do need to do through step 4 of that tutorial. After that, we can move into this folder number 2, which is the Ensemble, and move into the production folder. So from here, what we want to do is we want to prepare a number of input files and directories that will be used for the Ensemble modeling. So in this case, we use 16 replicas. You can change this value here during this input script to change with the number of replicas that you want. In theory, more replicas are better. Well, more replicas will be better, but if you don't have access to the ability to run 16 replicas, you can run as many as you need, or can. And this is done. First, we run this prepare plumed input script, which is really just a bash script that is going to, again, take all these values that we've been using before, the resolution, the best scaling value, the integral of the density, and it's going to create a number of folders with appropriate plumed input files, like we used in step 4 of the previous single structure process. It's going to take structures from the entire trajectory of the step 4 process. So if I go, I don't have it here. So I think actually we have 2 replicas in this, replica 1 and replica 2. And each of these will be we'll have a number of different files. You'll have your plumed ME data file, which will again be made for you by running the script. It will contain, it will be used, the initial structure will be a singular frame from the uncertainty ensemble that you generate in step 4 of the single structure refinement. which is, again, this is chosen automatically for you in this script. So it will go through, pull out an initial confirmation from that structure based on the number of replicas that you're simulating, and it'll start running the simulation based off of that. So again, you prepare your simulation using this. All you have to change is the number of replicas you want to run, and then you will run this 10 nanosecond long simulation in parallel using that number of replicas. This can be expensive, but we see that you don't need to actually run the simulations for that long to get a converged value or good quality ensemble, which is, I think, a huge plus. In this case, this is going to be running the same format that we did before, except now it's going to be using the meta inference framework that Max had talked about last week. Finally, we then move on to the post-processing and validation step, which is the folder 1. So here we were in folder 0, which is production. Now we move into folder 1, which is the analysis. And first script here that we run is the prepared plumed ensemble analysis script, which is, again, just going to, first, this is going to concatenate all of your trajectories together from all of your replicas, because the structural ensemble that we generate during step 0 here, the production run, the final ensemble is actually a combination of all of the individual replicas. They collectively make your structural ensemble. So we first concatenate all these trajectories together into one single trajectory. We then again fix any PBC boundary issues to make the molecules whole using Plume driver. And then we extract only the atoms that we want to use to generate the Cryo-EM density map as we had done before, which is, in this case, what we have specified before, called system map inside the index file. We then output this to a file called conf_map.pdb. From here, the procedure ends up being very similar to the procedure in the single structure refinement. We then align the whole entire trajectory using the transformation that we had done earlier. So we align the trajectory to the deposited Cryo-EM density map using this align.xtc or align.xtc.py script. We then add a B factor column to the reference PDB, which is our conf map PDB structure. These factors are going to be the same for all the residues, which they're done. We set this before doing the ensemble modeling, which is, again, the value is going to be equal to the minimum value that we found in the single structure refinement. We don't want a huge B factor value. We don't really want to be sampling the B factor value here because we have the structural ensemble in this case that is taking care of this uncertainty. The structural ensemble is a measurement of our movement in the Cryo-EM density map. And lastly, we can then calculate the CC mask score or CC mask like score on the original PDB and compare it to the CC mask score that we calculate for our structural ensemble. So it's the CC mask score for our entire ensemble. So I had done this as well. I can show the results here. So what we have here on the very left in this light green is the deposited CC mask score for the single structure. We then have our refined CC mask score, which we do see a little increase in the quality of the fit to the experimental data. And then we have our ensemble on the far right here, and we see a significant increase in quality, I think something around 14% compared to the single structure deposited model. So overall, I think we do end up fitting the Cryo-EM density significantly better than the single structure model, even for such a high resolution map. There's lots of things we can see here. Let's see if I can find the snippet of the structural ensemble once it's run. Yeah, so here I have the output of the structural ensemble. However, it's every 1,000 frames of our structural ensemble, so that we can see some movement. Whoops. And so this is our structure overlaid with itself every 1,000 frames. If we show this with the Cryo-EM density map, which again needs to be zoned, so we're not viewing all that extra density, and we can change this transparency to something very low to see. As we change the density threshold to lower and lower values, we can see that areas with low density, so where these areas here that have quite low density, end up corresponding to larger movements within our structural ensemble. And again, right now I'm just showing the backbone. If we want to show some chains, let's just select all aspartic acids and show these as sticks. We can also see the distribution of these side chains and their orientations throughout the structural ensemble. So in this case, depending on how your density is, if the structure is very stable, if there's a lot of density, you might have one state. And this one state may be very close to the state that's found in the deposited structure. However, in some cases where there's not a lot of density, particularly for large side chains such as lysine and arginine, you might see that there are multiple states occupied. And in theory, what you can do is you can calculate the distribution of these states. Again, it's really to highlight that these structures, even at high resolution of 1.9 angstroms, are not necessarily best fit by a single structure, but rather by an ensemble of structures. I think that is it. If there's any questions from the audience.
Well, I'm actually, you were super clear, so no questions here.
Okay. Okay, so I just hit home one more point. Again, the structure that the trajectory that you generate in step 4 during the first tutorial is really an uncertainty ensemble. This is not your structural ensemble. You cannot do analysis of side chain distribution or loop distributions and say that corresponds to the actual the structural ensemble of the protein. It does not. This is an uncertainty ensemble. Getting the structural ensemble is through the second tutorial, which is really using this meta-inference EMIVOX system. From here, this entire trajectory ends up being your structural ensemble, the final concatenated trajectory.